lesson, we got reduced row A and row B density matrices for a physical system consisting of 2 qubits. And now let's consider their properties. It should be noted that all these properties will be true for arbitrary reduced density matrices, and it is not difficult to prove them in the general case if we act in the same way as we did when we consider the properties of an ordinary density matrix. So, the first property, the resultant density matrices are self-adjoint operators. Let's consider a density matrix, row AB, which describes some physical system and proves the properties of the density matrix of the subsystem A. Density matrix of the subsystem A, by the definition, equal to partial trace over the B subsystem of row AB. And like we've done it before, we can write sum of I equals from 1 to n, where n is the dimension of the subsystem B, of tensor product of identity matrix and vector xi I. Here xi I is the basic vector of subsystem B. On the matrix row AB and multiplied by identity matrix tensor multiplied by psi I. So the first property is that density matrix row A is self-adjoint operator. Now let's prove this statement. The Hermitian conjugation of operator row A equals to sum I equals 1 to n, tensor product of identity matrix and the basic vector of subsystem B, the row AB, and again. And we should take the Hermitian conjugation from all of this expression. So we can write the following: sum over I from 1 to n, I tensor multiplied by xi I, and with dagger row AB, the dagger and I on the bra vector xi I dagger. And it is easy to show that it's just equals to row A. The second property, like the density matrix of the whole system, the reduced density matrix of any part of it is a positive definite operator. So, to prove the second property of the density matrix of the subsystem A, let the set of vectors xi j be the basis for the Hilbert space of subsystem A, HA. And we can write that xi j row A xi j by the definition equals to sum over I xi j tensor multiplied by psi I. Here psi I is the basic vector of the subsystem B. Multiply it on the density matrix of the whole system, row AB, and again psi J tensor multiplied by psi I. So let's denote the product of psi J on psi I as the state vector n ij, and the set of vectors n ij is the basis for the system row AB, or the whole system. So we can rewrite this expression form of sum over I n ij row AB n ij. And since every diagonal element of the density matrix row AB is greater than 0, is non-negative, that this expression is also non-negative. The third property, the reduced density matrix for system B is not equal to the reduced density matrix for system A. However, if we take the trace of these matrices, we will get the same results. Now, we want to consider the third property of the reduced density matrix for the subsystem A, for example, and prove that the trace of row A equals the trace of row B. So, it can be done through the definition of the trace, partial trace operation, and we can write the following. Trace row row A equals to sum over J psi J row A psi J. And here the set of vectors psi J is the basis for the Hilbert space HA, the Hilbert space of subsystem A. And we want to rewrite this expression as following. S equals to sum over J, sum over K, the basic vector of the subsystem A, psi J, multiplied by basic vector for subsystem B, psi K, multiplied by the density matrix of the whole system, row AB, and again on psi K on psi J. That's a multiplication. So now we want to denote the tensor product of vectors psi K and vector psi J as state vector and Kj. So it's just sum over J, sum over K. The vector n Kj on the density matrix of the whole system row AB on the ket vector n Kj. And the state vectors n Kj is the basic vector for the row AB physical system, for the whole physical system, and this is just a trace of the density matrix of the whole system. In the same way, we could prove that trace row trace row B also equals to the trace row AB. The fourth property, the determinant of the reduced density matrix of system A is equal to the determinant of the reduced density matrix of system B. Здесь должен быть захват экрана. Very often in physics, it is necessary to consider not only the physical system itself, but also the environment with which it interacts in one way or another. In our constructions, system A is the physical system of the interest, and system B is the physical environment of this system. As a rule, we cannot say anything about the quantum state of system B, because it is, in fact, the rest of the world, which consists of a huge number of the most diverse physical objects. In this connection, in order not to consider the environment, we actually need to average over all its basic states the density matrix ρ AB of the entire system that uses the procedure described above. Note also that if we consider a composite physical system consisting of systems A and B in a separable state, then if we want to consider only system A taking partial trace along the basic states of the system B, and the transition to the reduced density matrix of system A is natural step by step. In fact, separability means that the physical systems that make up the composite system are not related to each other, that is, do not interact with each other or are otherwise isolated. In this case, after taking a partial trace of the density matrix of the entire system ρ AB, we will not lose any information about the state of system A. The situation is quite different if we consider a non-separable or quantum entanglement physical system. In this case, when taking partial trace on the basic state of one of its parts, for example system B, we lose some information about the system A. The state vector of the density matrix of the physical system contains some general information about the state of the system of which it consists. Next week, we'll look at this using the examples of so-called Bell states, also called EPR pairs. That's all for now. Thanks for your attention.